All right, in this video we're going to look at radical halogenation and compare what happens. So let's start with methyl, and we're going to look at what happens if we react it with iodine and H nu, if we react it with bromine, if we react it with chlorine, and if we react it with fluorine. So in each case, we're going to look at what happens when we react methane with a halogen and a halogen radical. So first, let's look at iodine. If we react with iodine, the activation energy is really high, the intermediate is very unstable, and even the product is much less stable. So here at the end, we end up with CH3I plus HI plus an iodine radical. I'm not going to draw all the products for each one. I'll just draw the main organic product. So that's if we do iodine. If we do bromine, the activation energy is much lower, the intermediate is reasonably stable, and the product is on similar stability with our starting material. If I then switch to chlorine, again, it's more stable, and actually the products usually are going to be more stable than the starting material. And in the last case with fluorine, very low activation energy, the intermediate is even more stable than our starting material, and the product is really, really stable. And what that means when we look at all of these is that the iodine is so slow and so non-reactive that this is not a very useful reaction. The fluorine is so reactive that it's explosive and also not a very useful reaction. So in the middle is where we're going to work, and that is with the bromine and the chlorine molecules, with bromination and chlorination, because those can both happen on a reasonable time frame and can be reasonably controlled. So in the next set, we'll talk about the difference between chlorination and bromination. So now let's take a look at what happens when we do chlorination and bromination and what our products are going to be. So in the first step of this reaction, well, first chlorine will separate into chlorine radicals. A chlorine will come by and pull off a hydrogen, leaving a radical behind. And we can get this radical, but we can also have the chlorine come by and take off this hydrogen and form the primary radical. So we can either form the secondary radical or the primary radical. Well, now let's look at what the reaction coordinate diagram would look like for forming each of those intermediates. Okay, the question that you want to ask yourself is which one of these is more stable? And hopefully you looked right away and thought that the secondary radical is going to be more stable than the primary radical. So if I look at the reaction coordinate diagram, if this is the diagram for the primary radical, then the secondary radical is going to have a little bit smaller activation energy and be a little bit more stable. And now as these reactions continue, when this will finish with a termination step where they react with another chlorine radical, one electron each will come here. Here we get the secondary chloride. We can do the same mechanism here, and here we get the primary alkyl halide. Now when you look at these two, the secondary one is definitely lower energy, so you might assume that we get more of the secondary radical forming, which forms more of the secondary product. However, there's a statistical thing that's going on here as well, because if I look at this starting material, here I have 1, 2, 3 hydrogens, 4, 5, 6 that are at the primary position, whereas there are only 2 here that are secondary. So if I look, if they made the exact same energy and they had the exact same likelihood of forming, you would think that we would get a lot more of them happening at the primary because of it being more common. So that would, you might guess that secondary would be more. From statistics, you might guess that primary would be more. And in the end, what it turns out is that you get pretty close to a 50-50 mixture of the two. So what you're balancing here is you're balancing stability with statistics. Just what the likelihood is that any specific proton will be, or hydrogen will be removed by halogenation using radicals. All right, so let's look next at what happens with bromine. Okay, so before I start, try and see if you can draw the two initiation mechanisms where the bromine radical reacts with the propane, and then pause this while you're doing that, and then watch to see if you drew them correctly. So this radical comes over, this bond breaks, one of the electrons goes here to form a secondary radical, and this electron comes over, this bond breaks with one electron going there and one electron going here to form the primary radical. All right, now if we look at this, see where we start to form the primary radical with bromine. If I look at the secondary radical, it's actually much lower energy. So now there's quite a bit larger gap here in energy, transition state energies, as well as the energy of the intermediates between the primary and secondary. That's going to be important later on. So again, try and see if you can draw the second part of the mechanism where it reacts with a bromine radical and a termination. Here I have the primary, and here I have the secondary. So now, because there's a large difference in the energy barriers, the selectivity is much higher, and the secondary, which is more stable, is much more favored. So it ends up being about 96% to 4% of the secondary with bromination. So in bromination, what we find is that the reaction is much more selective. We get the most stable product, forming primarily. Whereas in chlorination, it's much more reactive, less selective, and we get a larger mixture of products.